So last time we talked about conservation of mass, and you want to use conservation of mass whenever you're trying to find a velocity or a flow rate or a mass flow rate. We're going to start conservation of linear momentum now, and linear momentum, this equation, is what you want to use whenever forces are involved. So you've got some forces, or you're trying to find some forces or moments. That's when you want to think conservation of linear momentum. Okay, so there are different forces acting on whatever control volume you're looking at. You're going to have pressure forces, you're going to have shear forces, you're going to have gravity forces, and also forces if there's any solid objects in your control volume. There's also, on top of all those other forces, are forces just to velocity coming in and going out of your control volume. So if you have, say, water coming into your control volume, it's going to have momentum with it, and that is going to be imparted to your control volume. And the same thing if you have some fluid going out. Doesn't have to be water, any fluid. So if you think about it, let's think about a fire hose. So let's say you have a control volume drawn around you and a fire hose is being shot at you. The jet of water is going to impart a force toward you if it's heading right at you. On the other hand, if you're holding a hose and the jet's leaving the hose, again, the force is still toward you. This is really weird, right? Because now the velocity is going the other direction, and yet you're still getting a force towards you. Okay, so the force is in the same direction, coming in or going out. Isn't that weird? But that's because if a flow is coming into a control volume, you end up with a force due to that momentum of that fluid coming into the control volume in the same direction as velocity, but if it's going out, it's in the opposite direction of velocity. And that way, that means that if that fluid velocity is going in the same direction, it's going to act differently if it's coming into the control volume versus going out of the control volume. Same thing with, you can think about that with solids. It works with solids as well. If you shoot a gun, you're going to get a recoil backwards, right, as that bullet goes out. It's the same, it's Newton's laws, equal and opposite reaction for every action, right? So what I'm going to do here is kind of generalize where we're going. So give you the simplest equation that we're going to get down to, and just kind of go through the problem solving method before we actually go back to the generalized equation and get into the harder problems. So at least you'll have an idea what these problems are about before we really get into the nitty-gritty of them. Eventually, so we'll start with the simple case, then we'll go do the general case, and then we'll talk about the forces, those pressure, shear, gravity forces, etc. And then finally we'll talk about what happens if the control volume is moving, and we'll do that in another class period. Okay, so starting with the very simplest case of our control volume equation. So remember, all your forces, all those pressure, shear, etc. forces are still there, plus you have the velocity forces, the momentum due to velocity. So the way we can write it is the sum of the forces, and those are those pressure, etc. forces, are going to equal the sum at the outlets of m dot v minus the sum at the inlets m dot v. Those are dots. Okay. And what that sum of the forces really is, the way this has been set up sign-wise, is those forces are the forces to keep your CV from accelerating. Okay, so if you did have an accelerating control volume, what you would do is take those velocity forces and put them on the same size as your sum of the forces, and then you set that whole thing equal to m times mass times acceleration of your control volume. So we're going to start with non-accelerating control volumes though. So this equation that I just wrote, this control volume analysis equation, that's what we'll use a lot of the time, but that's just when we have these simplifying assumptions. steady state, incompressible, and the velocity is not changing much across the inlets and exits, so therefore we're using average velocity. So these V's represent average velocity, and yet they're still vectors, okay? So they still have direction even though they are just average velocities as opposed to a velocity profile, okay? So again, we're going to have all these forces in here, pressure and forces and so forth. Whenever we draw a control volume, one of the things we want to do is get rid of our shear forces. So we never want to draw our control volume like inside a pipe. We want to draw it outside the pipe, and we want to draw our CV perpendicular to the flow at inlets and exits. And the reason that gets rid of shear is because shear is always that parallel stress, right? Shear stress is parallel. Tau x parallel. So if we don't have any component of our control volume going parallel, we eliminate shear stress, and we can just use pressure, which is much easier to deal with. Okay, so the idea is don't draw, if you have a flat plate or something, don't draw your control volume right along that flat plate where things are flowing, unless you're trying to find shear stress, and that would be different. Okay, so that's a little key there in how you draw your control volume. So what you want to do is start with a picture, and on your picture you are going to put in a coordinate system. Could be rectangular, could be cylindrical. You also want to label your inlets and exits. That's very important. Okay, so whenever you're doing these problems, start with a picture. A lot of times you have a picture already and you can just draw your coordinate system and label the inlets and exits. Then you want to make your assumptions. So some of these things up above here, steady state, incompressible, average velocity, fixed inlets and exits, those are your typical assumptions. Draw your control volume on there, and again, go perpendicular to the flow and also outside the flow. And you want to draw it where pressures are known, because that's going to make your life easy as well. You also need to draw a free body diagram. You can do that as a separate picture or right on that same picture if you have room. And then at that point you'll usually have to sum moments or forces, or usually use the equation we had that the sum of the forces equals sum of the m dot outs times v minus sum of the m dot ins times v. And finally answer your question. So let's just do an example. So this is all about the problem solving technique, assuming we can get to that simplest of conservation of linear momentum equations. Okay, so here we have a jet of water. This is a jet of water, so this is a nozzle. And you got water going through it. And it's going to come out of the nozzle into the air, and it's going to hit a disc. This is a disc. Okay, and I'm going to bring a setup to class to show you this exact experiment. Okay, so our process here is, well, draw a picture. We got a picture. Let's put a coordinate system on, and since this is a disc and the water is going to actually be coming out all around here, it's not rectangle, it's not really splitting into two sections, it's splitting and going out in every direction radially. So what we'd probably want to do is cylindrical coordinates on this, so I would put a Z this way and an R this way. Okay, label our inlets and exits. 1 is our inlet. Our exit actually goes all the way around, so there's just 1. You don't want to label 2 exits here because those aren't really splitting, it's like all the way around. Our control volume we want to draw perpendicular to our inlets and exits. So we want to draw our control volume to go straight across those flows. And then out in the air. We don't want it, we would never want to put it right on that disk, in other words. And this control volume is going to cut through that bolt. Okay, so let's look at the question. Here's our control volume. Water jet shooting vertically upward, hitting a flat plate. It's a disc flat plate. Find the vertical force in the bolt that holds the plate. Okay, so another thing you want to do when you draw your control volume is make sure, if you're trying to find a force in this bolt, make sure your control volume cuts through that bolt. Okay, so now what we can do is draw our free body diagram. We can do it right on this if we want. So right where this bolt, or where this control volume cuts through that bolt, we're going to have a force due on the bolt. That's what we're trying to find. And that's really the only forces. P here, pressure force, force due to pressure, is actually going to be 0 because everywhere on this control volume, so I've drawn it outside on everything. I never cut through this nozzle. So our pressure force is going to be 0 because it's all at P atmosphere, right? So P atmosphere is going to act everywhere. It's all going to cancel out. So some of our assumptions assume we want to use the basic ones that we saw before: steady state, incompressible. We're going to use average velocity because we aren't given a velocity profile, so we'll use average velocity. And it says right here, neglect the weight of the water and the plate, so we'll neglect gravity. Okay, so again, our sum of our forces equation, our conservation of linear momentum, is going to be sum of our pressure forces, we have none, so that's going to be 0, sum of our what we're calling body forces or gravity forces, and since we're neglecting gravity, can't always neglect gravity. Sometimes that's the driving force. Shear forces, and we can always neglect our shear forces as long as we draw our control volume so it's cutting perpendicularly. 0 for our CV. And then what we have is other forces. Sum of the other forces. And basically you're going to get these other forces whenever your control volume passes through a solid. So right here we have our bolt as our other forces. Okay, and that is going to be sum at the outlets, m dot v, minus sum at the inlets, m dot v. Alright, so what we end up with is basically our force other, which is our bolt force, is the sum of m dot v out minus v in. Okay, remember this is a vector equation, so what we really need to do is split it up into its components. So let's look at the z direction. That's our most important direction here. Sum of fz equals, the way I drew this, minus f bolt. And that is going to equal our m dot vz out minus our m dot vz in. Okay, so since this is cylindrical coordinates, we don't have the u, v, w components for the I, j, k directions. Instead, what we have is, for cylindrical coordinates, our velocities, we usually call them Vr, Vz, and V theta. Alright, so here for our z direction we've got a Vz. Okay, so what we end up here with is f bolt Well, what do we know about VZ out? So Z direction, is any of our velocity going in the Z direction at the exit? It is not. It's all going in the radial direction. So we have a VR at the exit, but we don't have a VZ at the exit. So 0. So what we get is F bolt equals m dot VZ in. And our VZ in is just our V in. It's going in the positive direction. And that is equal to our Q over A1. All right. 4 gallons per minute over that area we get from that 1/2 inch diameter. Okay, so our m dot then is the other thing we need. M dot, well, our m dot is rho times Q, okay, or rho times V times A, however you want to look at it. I'm going to leave this in terms of Q because Q was a given here. That 4 gallons per minute is a Q. So what we get is F bolt equals rho times Q, that's our m dot, and then times Q over A1. That's our V. And so that comes out to be rho Q squared A over A1. All right. And that's, I'm not going to plug in numbers for that in the interest of time, but there's your one example. That's how you kind of go through these things. And the directions of the velocity is very important in these problems. So here we have another example. Okay, we got a curved plate. Same problem, but the plate is curved. So the water that comes in actually turns around and goes upside down. In reality, this, look, the water in the demo that we're going to do, it comes up in the center and then it splits and goes around. It looks more like an umbrella, but you get the same result this way, and it's just easier to visualize this way. So let's just do it as if the water's coming up the side and going around. Okay, same process here. Let's make our control volume. We want to make it perpendicular to inlets and exits. Cut through wherever we want to find a force through a solid object. So here's our F bolt still. Here's our inlet. Here's our exit. Okay, so doing the same thing, same assumptions. Let's write same assumptions. We're going to have our Z direction for our coordinate system. Z, and we'll make R, doesn't really matter, I'm not going to use R. Sum of the FZs, again, breaking it down to the components, you got minus F bolt again, and sum of the outs, M dot VZ, minus sum of the ins, M dot VZ. So what's different this time is now at our exit we do have a component. In fact, the whole thing is going in the Z direction, so we can't just cancel out our outlet M dot VZ. Okay, so if we look at it this time, minus F bolt is going to be our M dot times, and now really you got to take into account directions of things. If I made Z going up, well, at 2 our VZ is going down, so that's minus V2. Okay, and then minus our M dot, and at 1 the velocity is going in the positive Z direction, so we just leave it as V1. Okay, so what we end up with, so let's just make a little note here, going in negative Z direction. Okay, so what we end up with is our F bolt equals M dot times V2 plus V1. Well, we're going to say that assume the water jet stays at the same diameter, which means the velocity is going to stay at the same diameter because the flow rate is staying the same throughout. So that's going to equal 2 M dot V1, and our V1 to M dot Q over A1. Same thing we had before. So M dot is still rho Q. So our F bolt now is 2 rho Q squared over A1. All right. So what turned out to happen is that the force in the bolt is double for the curved plate than it was for the flat plate. All right. And this actually makes sense because the plate is having to turn the water further than it did in the first case. Okay. So we'll try this in class, and it should work out that, yeah, the curved plate has about twice as much force as the flat plate. So stop here and do questions 1 through 2.